Hello. In this video, we're going to cover the Part 3 notes that was meant to be covered in lecture this week since we will not be meeting in person. Part 3 is the last part of Unit 1. And in these examples, we expect to cover some material from our one-dimension and two-dimension kinematics, as well as a discussion of some vector math. So before we get started, let me jump out to Schoology here. I'm still getting caught up on the assignments that were turned in over the weekend, so thank you for all of the work that you've submitted. One of the documents that you need to be referencing during this assignment and practicing with while preparing for the test next week are the formula sheets. If we jump into the course documents and look at option number 6, formula sheets, I've got a Word document that has a list of several formulas, and these are quite helpful for our kinematics work. But also, I think we could add a couple notes to this, and I'll do this in Monday's class, but a couple notes on the vector math, the component method, and then the oblique method for finding the results of a resultant vector. So for today, I think the information that's posted here is sufficient, but for next week and in preparation for the test, we'll add a little bit to that. Additionally, the document that I'm referencing right now is also available, but the list of questions that I've posted are in Unit 1, Part 3. And I need to move this. The update that I'm referencing was posted yesterday in class, or before class. And here's a little note about why class was canceled for this week in person, and then the list of the questions are posted here. So I think it would be a good idea to have these printed out so that you can work on them on paper, but it is certainly fine if you want to look at them on your computer screen and then do your work on paper as well. Keep in mind these notes are permitted for use on the test next Friday. Okay, and I've rearranged the Part 3 folder, so you should see that update towards the top now. One last thing that I wanted to remind you of is that you should be watching the Week 3 videos for clarification and some practice. So a lot of the problems that we're encountering right now are very, very similar to the questions that we see in Chapter 2 and Chapter 3. And again, these playlists here show solutions to every practice problem from the back of the chapter in the textbook. So my instruction is not the only one that you can be using for learning the content here. Well, let's get started. Here's problem number 1. Car travels 50 meters forward in 10.5 seconds while uniformly decelerating to a rolling stop with a final velocity of 1.5 meters per second. So the car did not come to a complete stop, but they almost stopped. They slowed down dramatically. We need to find the car's original velocity, and then we need to find the car's acceleration. Now remember, acceleration and deceleration mean the same thing. Generally speaking, though, acceleration can be, well, in this case, we're going to interpret this as a positive value, although acceleration could be positive or negative. This phrase, deceleration, clearly implies a negative acceleration rate. So one of the things that I like to do first is list what's given. And the first thing that we have here is the number 50.0 meters. And so if we read the context surrounding that, it says a car travels 50 meters forward. So if we're imagining a car, and it sounds like this is a 1D problem, there's no mention of it going up or down. We've got a car that's traveling forward. Well, it started at some position and it ended at some position. And the difference between the two is the displacement. So I'm going to label delta x as 50.0 meters. And of course we'll label this as a positive value because it was clearly indicated that we moved forward. It took 10.5 seconds to do so, so the amount of time that has passed, or delta t, is 10.5 seconds. The final velocity is 1.5 meters per second. So I'm going to mark this as velocity final 1.5 meters per second. and it was 1.50. So for those of us that are concerned about significant figures, it looks like all three of these have 3 significant figures. So that's worth noting. Our goal, or what we need to know, right off the bat, we need our initial velocity. So that's what we're looking for. I'll put that up here a little bit out of the way. Initial velocity is what we need to know. And then in the second component, we need to know the car's acceleration. So the acceleration is unknown. Now in this situation, we'll go ahead and mark that as average acceleration. And that's because the instructions did clearly state that we're talking about uniform deceleration. So it's not changing its acceleration as it slows to a rolling stop. Now, what I would do from here is look at the formula sheet, and I would try to find a formula that utilizes these components over here. Let's also keep in mind that delta x could be considered x final minus x initial. So position, final position minus the initial position is another way to write delta x. And same thing with delta t. If we find the final time minus the initial time, that's the same thing as delta t. So if I see an equation on the formula sheet that has this or this, that also contains either the equation here or delta t, along with a final velocity, and our initial velocity, if we have that value, then that's probably going to be the formula to use for part A. So I'm looking at this group here, and you may notice that there's a group for motion in x direction. So that's a good place to start. And while we're looking at it, I do want to point out motion in the x direction and motion in the y direction are calculated the exact same way. When we need to be specific, we just use different subscripts indicating horizontal movement or vertical movement, essentially. So a more generic form of these equations might be something like this. We might say velocity in general is equal to the initial velocity plus the acceleration times time. And this summary equation represents this first row in either the x or the y direction. So if you want to add this to your list, that would be perfectly fine. Or at the very least, just make a mental note that these subscripts aren't necessary. The general form works just fine when talking about motion in either a vertical or horizontal direction. But anyway, back to the question at hand. Here's an equation that might be very helpful for us. We've got the change in x equals a half times the velocity in the x direction. Now, the subscript f was not included here, but we could include it because that's implied in this equation. So the final velocity plus the initial velocity times the amount of time that it took to get there. So we've got a delta that's implied there as well. So I think this is the formula I want to use. So let's jump back over here. And I've just rewritten the equation, and we'll start filling in some values. Notice I've updated the equation with the components that are more closely indicated here on our given information. So I've made the substitutions here, and it's really important to include your units, so let's get in the habit of doing that. We've got 50.0 meters equals 1/2 times 1.50 meters per second plus v naught, our initial velocity, and it is in the x direction, but I dropped the subscript x, and that's okay. Multiplied by 10.5 seconds, the amount of time that's passed. So there are a few algebra steps in order to solve for v naught here, in order to get it by itself. We could multiply both sides by 2, divide both sides by 10.5 seconds, and then subtract 1.5 meters per second. So I like to make a mental note of that and a map, if you will, of the process that we're going to go through to get v naught by itself. And me personally, I like to do all of the work in one step on my calculator. So I put ... here because technically you could do the work in several steps, but if you think about it in a single step and include your units when you rewrite this, then you should be well prepared to see the result and the unit that comes with it, and you should recognize whether or not the math that you're about to do is appropriate for the situation. And as far as the setup goes, this is exactly what I mentioned a minute ago. We're going to multiply by 2 to eliminate the 1/2, then divide by the 10.5, and then after that's done, we're going to subtract the 1.5 over. Now, if I'm looking at my units, we have a meter value that gets divided by a second value. So we've got meters per second in this term. We're going to subtract a term that's also meters per second so that I know my result is going to be some value in meters per second, which is good because the answer that we're looking for is velocity, which is a measurement whose unit is meters per second. Now, as I go to the calculator, I'm going to set up the equation exactly as we have it written on paper without the units. And I don't need to include all the extra decimals. That's good for significant figures, but we can interpret that mentally rather than relying on the calculator. So we've got 2 times 50 divided by 10.5 minus 1.5. And it looks like 8.02, etc. is the result. Now, all of our values along the way contain 3 significant figures, so that's what I'm going to use here. There's no rounding necessary in this case, so I'll report this as 8.02 meters per second. Moving on to the next example, we need to know the acceleration. Well, here again, I'm going to look at the formula sheet, and I notice there are several equations that do involve acceleration. And certainly we could use this first equation right here because we now have all of the components. We just computed the final velocity. We were given the initial and we were given the time, and we can calculate A. And similarly, the others all essentially would give us the same thing. So I'm going to use this first example, and the reason why I'm doing so is just because it's a little simpler to work with. So the final velocity is equal to the initial velocity plus acceleration times time. And I think I said this backwards a minute ago. We calculated the initial velocity, so that's the value I'm going to put on the right side, and we were given the final velocity. So with our values substituted, we'll have a little bit of algebra ahead of us. Now again, I'm making a mental note here. I would like to subtract 8.02 to the left-hand side and then divide that result by 10.5 seconds in order to isolate A. And so I recognize across the numerator our unit is going to be meters per second after I complete that subtraction, and meters per second is being divided by seconds again, so we can report our unit as meters per second squared, and that's exactly what we're going after for acceleration. So off screen I got a decimal value that's a little bit longer than 3 places. I'm only going to retain 3 of them, and in this case I do have to round, so I'll call this 0.621 meters per second squared. So there we go. Now that's the technique that I would use for completing all of these problems in the handout today. So let's pick up the pace just a little bit, and we'll see if we can finish some more of these a little bit faster. In problem 2, a projectile is forced out of an air cannon with an acceleration of 7.1 e5. Now remember, 7.1 e5 is the same as scientific notation, 7.1 times 10 to the 5th power. It took 6.27 e negative 4, or 6.27 times 10 to the negative 4th power seconds to exit the barrel. And our job is to find the final velocity. So as far as given information goes, we know the acceleration, we know the time, or delta t if you prefer, and we know the initial velocity is 0. Now it's not written anywhere in here, but it's implied that the object was at rest at the beginning. And what we need to know in this case is the final velocity, or the velocity at the end of the barrel. So the formula I'll use here is the final velocity is equal to the initial velocity plus acceleration times time. Now there's no real algebra that needs to go on here. We've already isolated the variable that we're going after by using that formula. So we'll just execute this. Now I do want to point out that on this calculator we do have a key specifically for scientific notation. So if I would like 7.10 times 10 to the 5th power, then all I have to do is write the 7.10, tap this double E key, and now we've got our scientific notation. we don't have to bother with the times 10 and then raise that to an exponent. And then we're multiplying this value times 6.27 times 10 to the negative fourth power seconds. So we had a 0 plus this, so the only math that's necessary is the product of the two. And it looks like 445.17 is going to be the result. Now with significant figures, it looks like there were 3 in each of these, 3 sig figs, 3 sig figs, and so our answer should contain 3 significant figures as well. So we'll say 445 meters per second. And I know that's the unit because we had a unit of meters per second here, summed with, well, this was meters per second squared, but we multiply that by seconds. So our unit, if you want to think of it this way, is meters per second squared times seconds, which could be written as a fraction over 1. One of these seconds cancels one of those, and our final unit is meters per second, what we were after. So I think this is a good result. In number 3, we have a drumstick that collides with a drumhead at a velocity of 27.2 meters per second and stops after stretching the drumhead a distance of 1.5 centimeters. So if you can imagine this impact, this 27.2 is going to represent our initial velocity. That's the velocity as the drumstick initiates contact. And then it's able to move this drumhead another 1.5 centimeters. So we've got this change in position. I'm going to use actually Y here, because when you're thinking of a drumhead, at least when I think of a drumstick and a drumhead, the stick is moving vertically. And it stops, so we can't ignore this. So after the collision is had, the drumstick comes to a stop, and so that tells me that its final velocity is 0. And we need to find the rate of deceleration of the drumstick. So that's the value that we need to know in part A. And the question also becomes how long, as a measure of time, how long does the impact last? How long is the drumstick in contact with the drum head? And so that's a T value that we're after. And so as I was reporting my given information, I just recognized something. Maybe you caught this. The change in Y was measured in centimeters while the velocity values were given to us in meters. So we better make sure that our units agree and match. So what I'm going to do is I'm just going to do a quick mental computation. 1.5 centimeters divided by 100 will give me the value in meters. So I'm going to report this as 0.15 meters. So in part A, we need to know the acceleration, and I think an appropriate formula is this one here. So I'm looking at the right-hand column for our delta y values this time, and I know we have our final velocity, our initial velocity, and we have our change in height in this case. All of that information provided will allow us to solve for A. So after making our substitutions, we get this result. I'll make a plan for solving for A. Looks like we'll have to subtract 27.2 squared, then divide by 2 and divide by 0.015. Now if I'm thinking about my units, across the numerator I end up with meters squared per second squared because the measurement got squared, so our units also got squared, meters squared and centimeters squared. And then in the denominator I just have meters. So this division is the same as meters squared per second squared times 1 over meters. And now one of the meter units will cancel and we're left with meters per second squared, which is a measurement of acceleration. So our roadmap looks good. Let's go to the calculator and generate a result. And I did this off screen, and the value that I ended up with, including three significant digits, is negative 24,700, and our unit is meters per second squared. This result is negative, so that does imply a reduction in acceleration, or a negative acceleration, also known as deceleration. but it seems awfully large. So I don't know if our data was not realistic or not, but I'm fairly confident in the math we've done. So we'll let that stand, and we'll investigate it further at another time. In part B, we need to know the time that this drumstick is in contact with the drum head, so delta t, or t is what we're after. And after looking through the list of equations on our formula sheet, I've settled on this one here. Delta y is equal to 1/2 of the sum of the velocities times time. And we substitute our values into the equation and now solve for t. Now in this setup, our numerator is going to contain a unit of meters. Our denominator contains a unit of meters per second. When meters is divided by meters per second, we know our unit at the end is going to be seconds, which is exactly what we're after for time. And doing the computations on my calculator off screen, I get some extra decimals here, but we only need 3 of them. We're going to use 3 significant digits for these measurements, although there's some argument to be made that this one should have only had 2 because it started off as 1.5. But we'll ignore that for right now, and we'll say that there are 3 significant digits. That's going to help us with this result of 0.001 seconds. So the drumstick was in contact with that drum head for 1/1000th of a second. I think we'll complete one more example in this video because this sort of marks the end of the kinematics questions, and then we get into some vector math here. So this would be a good natural stopping point. And this one's kind of interesting. You drop a rock in a well and see the splash 1.25 seconds later. This would be a whole different problem if you hear the splash, because then we have to introduce the speed of sound. But as far as the speed of light goes, for our intents and purposes, speed of light is virtually instant. So this will work for us just well. So 1.25 seconds later, we see the splash, and now we need to determine how deep the well is. So as far as given information goes, we don't have a whole lot to go with in the problem, but there is some implied information. And this one in particular is going to be very helpful. On Earth, we are going to use an acceleration of negative 9.81 meters per second squared to represent our acceleration due to gravity. All objects are accelerating towards the center of the Earth at negative, we're going to say negative because it's downward, 9.81 meters per second. It's a good thing that we've got other forces in play that are preventing us from falling down, because we are experiencing this acceleration at all times. Now, as far as velocity goes, one thing that's implied too is that this object was dropped. It wasn't imparted with any velocity at the beginning, so we do have an initial velocity of 0 meters per second. So what we need to know in this case is the change in y, because that's going to represent how deep the well is. What's the vertical difference between the rock's release point and its ending point? So which formula do you think would be appropriate in this case? Think about what's been given to us and what we need to find. Well, I don't know the final velocity of the rock, so I don't want to use this example down here or here, even though they both do contain delta y, which would help us in our math. But this one here does have delta y. It relies on the initial velocity, the time that's passed, and acceleration along with time again. So we have these values over here on the right-hand side. That should be sufficient for us to compute delta y. So again, here's the formula. I am omitting the subscripts y indicating vertical movement. I think that's just implied in the problem, and I'm perfectly fine if you do the same. And after we make the substitution, we don't have any algebra that needs to be done in order to isolate the delta y variable, but it is worth noting our units here, seconds in the numerator and seconds in the denominator, are going to cancel, leaving us with a term containing meters. And seconds squared here will cancel with seconds squared here, because that unit does square itself. And so again, we're going to finish with meters as our unit after the math is done, which is perfect because the distance that we're looking for is measured in meters. And we again have values that were given to us with 3 significant digits, so we'll go ahead and report our final answer off the calculator as negative 7.66 meters. Okay, again, this is a good stopping point for right now. The video is getting a little bit long, and we're seeing a natural change in the types of problems that are being addressed here. So let's pick up in the next video. Thanks for watching.